When last we looked at the atom, we were looking at J.J. Thomson's plum pudding model, where after the discovery of electrons, he stated that the atom is this sphere of delocalized positive charge, and that electrons were stuck in the atom like raisins in plum pudding. And so with this model of the atom, we move on to a student of J.J. Thomson's, Ernest Rutherford. Ernest Rutherford worked with J.J. Thomson at the Cavendish Laboratory. He moved from there to Australia, where he did some work, having been a native of New Zealand. And while he was in Australia, he did the famous gold foil experiment in 1911, which identified that there were other parts inside the atom. That gained him enough fame that when J.J. Thomson retired from Cavendish, Rutherford took the prestigious post as the head of the Cavendish Laboratory. But to his gold foil experiment, which is his greatest contribution to the history of science, the gold foil experiment was actually done with these two guys who worked for Rutherford in Australia, Hans Geiger and Ernst Marsden. Geiger, you will recognize probably as the creator, or at least the co-creator of the Geiger counter, which measures radioactive particles. And so it's probably not a surprise that the gold foil experiment employed radioactive particles. So here's how the gold foil experiment worked. They made a lead box because lead will shield radiation, so radiation won't be able to escape the box, and in there they put radium. Radium's a radioactive source, and it emits radioactive particles that'll bounce around inside the box, and then on one side of the box is a tiny pinhole, so that only particles bouncing around in the box that line up with the hole will escape. And what you get is a directed beam of radioactive particles. They essentially made a radioactive particle gun, which is super cool, right? And then what are you going to do once you build a radioactive particle gun? You're going to start shooting it at a bunch of stuff, because this is what scientists do. They discover a new technology, and then they go aim it at just about anything they can find. The gold foil experiment aimed the radioactive particles at, well, a thin sheet of gold foil. That is made of what? Gold atoms. We know the mass of gold atoms at the time. The mass of gold atoms is pretty significant, but their structure, of course, is just delocalized positive charge and electrons. So they shoot the radioactive particle ray at the gold foil. Because the atom is only made out of tiny little bits of electrons, and alpha particles are significantly bigger, the biggest thing you can expect the alpha particles to run into are electrons, and they should run them right over, and the radioactive particles should go right through the gold foil and light up across the back of the screen. Now they light up because the screen is painted with a fluorescent paint, so when the radioactive particles hit it, a little microscopic burst of light will be shown off. And so we can measure where those radioactive particles hit. And what we find is that the particles go through the gold foil like we'd expect, except that sometimes they don't. And it's the when they don't that tells us something about the atom that Rutherford was able to identify. This is what the actual apparatus would have looked like. This long protrusion on the left here is a microscope lens. So they're actually rotating that all the way around this inner chamber. This is the box containing the alpha particles. This is where the gold foil would be, here in the middle. The alpha particles shoot through the gold foil, and then you're able to rotate that microscope lens 180 degrees and see where on that screen does the radioactive particles light up. And of course, like I said, they expected all of the alpha particles to go through the gold foil and light up on the opposite side of where the radioactive particle gun is, because there's nothing in an atom that should be able to stop a radioactive particle, in this case what we refer to as an alpha particle. Well, real quick, what's an alpha particle? An alpha particle is a particle that contains 2 protons and 2 neutrons. Has a charge of 2 plus, and it carries a mass of what we're going to call 4 AMUs. AMU stands for atomic mass unit. Right now we can just use it as a relative source here. So an alpha particle weighs 4 AMUs. An electron weighs about 1 over 2,000 AMUs. It is considerably smaller. And if an alpha particle hits an electron going at full speed, it would be like me standing on a football field where a professional NFL linebacker runs at me at full speed and collides into me. And imagine what you think is going to happen there. That linebacker is likely to even break stride. I, on the other hand, will end up in the ground or on the ground, maybe in the ground, and shortly after that in the hospital. And so this is what we expect from this experiment. But we get this funny thing that every once in a while particles are deflected. Furthermore, some of them are deflected so much that they bounce back at the source of the particle beam. And this seems completely and totally impossible unless there is something very, very dense in the center of the atom. What is that thing? Well, Rutherford called it a nucleus. And from what we know of a gold foil atom, there are protons and neutrons in a gold foil atom, and the average gold foil atom is about 197 AMUs. And now it makes a little bit more sense that something that weighs 4 AMUs, as it's hurtling towards the gold foil, if it strikes that nucleus that weighs 197 AMUs, it would bounce back. Okay, so what does this mean at kind of the particle level? Well, if we assume a Thomson model, well, all of the particles are going to go through mostly empty space unless they bump into an electron. And if they bump into an electron, it's going to be like a fly hitting your windshield on the highway. And because of that, your expectation of the Thomson model is that all alpha particles are going to go straight through, and they're only going to light up 180 degrees away from the source of the radioactive particles. Well, because of the observations, so we start with a Thomson model for Rutherford. We expect a certain set of observations here on the bottom left. If you move to the bottom right, we get a completely different set of observations. Mostly what we thought we were going to get, some small deflections when things get near the nucleus, and complete reflections backwards when things hit the nucleus. And so what can we learn from these observations? Thomson says, well, there's a thing in the center that these things are either coming close to and deflecting or they're bouncing off of. And how they bounce off and deflect tells us something. So there are 3 primary observations and conclusions from the gold foil experiment. Most alpha particles pass right through the gold foil undeflected. Ergo, conclusion, the atom is mostly empty space or electrons, and neither of those things are going to change the trajectory of an alpha particle. 2, a small number of alpha particles get deflected when they get near the nucleus. Well, that tells us that atoms contain a small, dense nucleus because only every once in a while do things get near. And the conclusion for this one and the conclusion for the next one are kind of related, and we'll come back to that in a second. But mainly what we're saying is because it only every once in a while is deflected, well, that means this thing must be pretty dense, and it must be in a very small portion of the atom. And then very few alpha particles bounce back towards the source. This tells us that this thing is positively charged. And we know it's positively charged because if you get a direct hit here and this thing is negatively charged, it should stick to that nucleus because positive and negative charges would be attracted. Because it bounces off when you get a direct hit, that tells us that when they hit each other, they're repelled by one another. Now, the deflections can also tell us something about the charge, but only if we know how the alpha particles are approaching the nucleus. So in the diagram we have to the left here, as the alpha particles approach the nucleus, because they are repelled, that particle is deflected down. Were it deflected up, that would tell us that the nucleus is negatively charged because your particle, as it's moving really fast past the nucleus, is drawn towards it. Now, there's no way for you to know because you can't actually look at what's happening inside the atom. All we can look at is the result of the trajectory of those particles. So we've got mostly empty space, a dense nucleus at the center that's positively charged. And this is what we learned from the gold foil experiment. And so Rutherford has to redesign this Thomson model. It's not delocalized positive charge, it's focused positive charge. In the center of the atom, we refer to this as the nuclear atom, not because it's a nuclear bomb, but because it has a nucleus. And the electrons then are floating about on the outside. There's a famous line that Rutherford gives about this experiment. He says, "It was quite the most incredible event that had ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." And all he's saying is there was no expectation that there was anything inside the atom big enough to deflect an alpha particle. But of course, when you take all of the mass of an atom and you focus it at the center of the atom, and you take something like gold, which has a mass of 197, well, darn it, there is something pretty significant there that you didn't expect to be there before the experiment started.